Okay, so now that we've spoken about the intuition and the high-level idea behind converting an NFA to a DFA, we're actually going to look at the algorithm. So the algorithm is written down here. I don't think it's actually very useful for me to read through this and explain it as I read through it because it'll just be a bit confusing. So I'll let you read through the algorithm on your own time. I highly suggest doing this after you've seen me go through an example, because that's exactly what I'm going to do now, is I'm going to just talk about the algorithm while doing an example. So the following example is the one that I'll be talking about. Consider we have the following NFA N, so this is our NFA. We can clearly see that it's an NFA because if 0, 1 is our alphabet, we see that, for instance, Q0 has two choices to make when it's reading 0. It can either go back to Q0 or to Q1. We also say that for Q1, there is no transition for 0. Okay, and finally for Q2, there aren't any transitions for either 0 or 1. So actually, even before we talk about the conversion algorithm, what is the language accepted by N, right? Well, we can see that what essentially our NFA is doing is it's searching for a string, right? It's searching for a string. It's going through zeros and ones. It doesn't really care what it's seeing. But as soon as it sees a 0 and 1, it has the possibility of using these two transitions to go to Q2, which is a final state. But remember, the NFA only accepts the string if it finishes reading the whole string and it ends in a final state. And so what that would mean is that the 0, 1 would have to come at the end of the string, right? So this 0, 1 would need to be at the end of the string. So that is, if I have a string like W001, then you can imagine the NFA saying, okay, well, for the first 0, I'm going to guess that I'm going to go back to Q0. Then for the second 0, I'm actually going to go to Q1. And for the 1, I'm going to go to Q2. And so this leads to an accept, right? So 001 is accepted because, in fact, it ends with 01. But if we look at some other string, like, let's say this was W1, W2010, right? So there is a 01 here, right? So the NFA could guess, okay, well, actually, I'm going to start by going to 0 and to 1 using these two strings, these two symbols. But once I'm at Q2, I still need to read a 0, and I have no outgoing transitions. So I can't do anything. I'm stuck, and I jam. So that doesn't lead to an accept. If I read the 0 here, and then the 1 here, once I read this final 0, I get to Q1, but that's not an accept state, right? So the only way for me to actually get to an accept state would be if I had an extra 1, right? Because then I would actually end with 0, 1, and that would lead to an accept. But the string, as it is right now, would be rejected. Okay, and so it looks like the language accepted by this NFA is actually all strings in 0, 1 star, such that W ends with 0, 1. Right? Hopefully, you've seen enough NFAs or DFAs at least by now to kind of recognize this pattern. And you can see how writing an NFA was a lot more convenient, right? So you can see, again, the witness, but you can see again the convenience that NFAs bring us. So instead of like having all these extra transitions, so maybe if you have a 0, you have to start your search again. You don't really care about those edge cases. All you need to say is, well, I'm looking for a string, and then I'm going through a string, right? So I'm going through a string. Once I end with 0, 1, I immediately transition to Q2, right? So this is the convenience of the NFA. Okay, now how do we actually convert this NFA to a DFA, okay, such that the languages accepted by both are exactly the same. So remember, this means exactly the same, right? So M should accept all and only all the strings accepted by N, okay? Well, let's walk through the actual algorithm. So the very first step in converting an NFA N to a DFA M is to create an initial state. So step one is going to be creating an initial state, which we'll call S0 for the DFA M. And what the initial state is going to be is it's going to be a set. S0 is going to be a set which only contains the state Q0. So it contains the initial state of the NFA. Okay, this is how we start, because when you start the computation of an NFA, you always start with the single initial state, right? So you start with the single initial state, and now we need to create transitions, right? We need to create transitions for the DFA. So step two is going to be creating transitions from S0, right? Based on the transitions in the NFA. Okay, right? Because we're converting the NFA to the DFA, right? To a DFA. So the converted DFA has to faithfully represent what the NFA is actually doing. Okay, and how do we do that? How do we actually do step two, right? So to do step two, for each letter that can be read, right? So for each, let me say sigma, I'll write sigma as a letter in the alphabet. For each letter in the alphabet, we need to find the states that are reachable from Q0. So find states reachable from Q0 in the NFA while reading the letter sigma, right? So what I mean by that is, if I'm at Q0 and I read a 0, I can either go back to Q0 or I can go to Q1, okay? And so what that means is that from Q0, from the set Q0, so from the set Q0, in the NFA, when I read a 0, I can either go to Q0 or Q1, right? And so I represent this choice as a set, right? And this, because this is a state in my new NFA, you can see why this other set would also be a new state in my DFA, right? So I meant to say this is my new initial state in my DFA, right? Sorry, I made a mistake there. This is the new initial state of my DFA. Now this will become a new state in my DFA, okay? So the set, right, is actually going to become a state in my DFA because it's representing all of the possibilities. Remember, the intuition is that I want to include all of the possibilities that existed in my NFA into a single state in my converted DFA, right? And so that's why here, if this is the new initial state of my converted DFA, you can think of this as another new state in the DFA. So we can call it, let's say, S1, right? And then we have to do the same thing for each letter in the alphabet, right? So that was for 0. We can also do the same thing for 1, right? So if I'm at Q0 and I read a 1, where can I go? Well, the only place that I can go is back to Q0, right? So it's back to Q0. So here you can think of this as a state in the DFA. Once it reads a 1, it just goes back to the same state, right? So the conversion really is just a matter of understanding that the sets which are returned from the NFA's transition function, once you take the union of all the sets, accounting the union based on what states are in the initial set, okay? When you take the union of all the possibilities, which are sets, right, that gives you a new set, and this new set becomes a state in your DFA, okay? So formally what this actually looks like is, like I said, you begin with the start state being the set containing the set containing the start state Q0, right? And then for each letter in sigma, okay, you find all the states that can be reached from S0, right? So this delta star is the new transition function for the DFA, the converted DFA M, okay? This is state, the initial state in the DFA, okay? And this is just the letters that it's reading, right? Okay, so we see that once it reads the letter 1 from state S0, it just gets back the set containing the state Q0, which is actually the same state that it was at previously, right? So you could also have written this as delta prime S01 gives you S0, right? But if you read a 0, instead what happens is that you can go to 2 different states. You can either go to Q0 or to Q1. And so this becomes a new state, okay? And the idea behind the conversion algorithm is you repeat this procedure, repeat this process on every newly, let's say, generated state. So what I mean by that is now that Q0, Q1 has appeared, right? I've generated a new state. I need to repeat the same process on Q0, Q1, right? So I have delta prime, Q0, Q1, or again, we could have also just assigned this to the state S1 in the DFA. When you read a 0, what can happen? So now this is where you have to take the union, right? So what you're doing is you're going to take the union of delta Q0, 0 and delta Q1, 0, right? So just a reminder, this is the transition function in the DFA that you're creating M, and these, well, the deltas are the same, right? This is the transition function of the initial NFA N, right? So this returns a set of states, and this returns a state, okay? So the only conversion that's happening is that the set of states is going to become a state in the DFA, okay? And so what you'll notice is that delta Q00, well, we already know what that is, right? That's when you're at Q0 and you read a 0, you can either go to Q0 or Q1, right? Union, when you're at Q1 and you read a 0, you can't go anywhere, right? so you can't go anywhere, so you union with the empty set, right? But Q0, Q1, union the empty set is Q0, Q1, right? So this is empty because if I'm at Q1 and I read a 0, I can't go anywhere, right? So the transition function in the NFA is going to be empty, okay? So that's for the letter 0. What about the letter 1? Well, it's the same thing, right? So for the letter 1, I'm at Q0, Q1, and I read a 1, right? So I repeat the same process, okay? So now it's the union of Q0, 1, union Q0, Q1, right? So again, remember this is for the newly created DFA, and this is the old transition function in the NFA. Okay, so when you're at Q0 and you read a 1, you can only go to Q0, so you get the set Q0. And then when you're at Q1 and you read a 1, you go to Q2. Okay. So what you actually get is a set containing Q0 and Q2, and this is a new state. This is a new state. Okay, and so again, you're going to have to repeat the process, right? So now you repeat the process on this new state Q0, Q2, and you do this until you have no more new states that are generated, right? So that's what's done here, right? Now it's just done in a much more compact and tabular form, right? So this is definitely much clearer than the drawings I did here. So the column here is just the states that are the new states that are generated that are going to appear in the DFA, right? So this is for the DFA M. This is just a union. This is the union I was talking about before, right? So if I'm in this state in my DFA, the state I go to in my DFA is the set of states that I can go to in my NFA. And that's represented by the union of the states, right? It's represented by the union of where I can go to in my NFA. Right, so this is just a compact way of writing. So essentially, you can just think of this as this is the union operation. So it's kind of like a sum or a sigma operator, where instead of doing a summation, you're doing a union, right? So this is saying take each state in the set S, right? So this could be the set S, and then give me all of the states that I can reach from that first state when reading a 0, right? And then you repeat this this process for each of the states in the set S, right? Because remember, the state S S is a state in the DFA, but it's also a set of states in the NFA, right? So that's why I'm kind of using the terms interchangeably. Okay, and so this is for the letter 0, and then this is for the letter 1, right? So this is actually from step 1 and 2. This is from step 3. It's what we just wrote previously here, right? So we said that if we're in state Q0, Q1, and we read a 0, we go back to Q0, Q1, and that matches up with this. And we also said that if we're in the state Q0, Q1 in the DFA, or if we're talking about the set of states Q0, Q1 in the NFA, we go to the set Q0, Q2 in the NFA, right, the set of states, or we go to this new state in the DFA, right? And so that's why we have Q0, Q2. And then again, we repeat the same process, right? So here we have the set Q0, Q2. What happens if I read a 0? So from Q0, I can either go back to Q0 or to Q1. So that's when I read a Q0. That's when I'm at Q0 and I read a 0. If I'm at Q2, and I read a 0, I get the empty set, right? I don't go anywhere, right? Because there are no outgoing transitions. So you can think of this as just being Q0, Q1, union the empty set, right? And then similarly for when you're reading a 1. So when you're reading a 1, you take the union of when you're reading a 1 and you're in Q0 in the NFA, and when you're reading a 1 and you're in Q2 in the NFA, right? Well, when you're in Q2, we already know that that's the empty set, right? Because again, there are no outgoing transitions from Q2. When you're in Q0 instead and you read a 1, the only thing you can do is go back to Q0. Right, so we have Q0, the set Q0, union the empty set. And so we get these two states. Because there are no new states are created, we're done with this procedure, with this process, right? So you can really just think of this as kind of like adding stuff to a table, and then as long as you're adding more stuff, more new stuff to the table, you're repeating this process, right? And so once you've done that, now we can actually build the DFA, right? So we can build the DFA. So here I've just replaced the notation of taking the union of the states in the NFA to what it means for that transition in the DFA, right? So what I mean by that is these are the states in the DFA, right? So these are the states in the DFA. So you can think of this as the new set of states Q prime, right? So maybe this is S0, this is S1, and this is S2, okay? And then for each of these states, when I read a 0 and when I read a 1, I go to a state in my DFA, right? So I could have just rewritten this as, instead of the set Q0, Q1, I go to S1 and then S0. And then instead of Q0, Q1, here I could have written S1 and then S2 here. And then here I could have written S1 and S0 here, right? So it's just a matter of relabeling the states, right? So then once I have the transition function, right? So this is the transition function for the DFA, okay? I can also represent this graphically, okay? So I see that this is my initial state, right? When I read a 1, I know that I go back to myself. When I read a 0, I go to Q0, Q1, right? Or again, you can just think of this as S0, S1, and S2. The same thing for the state S1 when I read a 0 and a 1, and the same thing for state S2. And then this is definitely a DFA, right? Because for each state, you have exactly cardinality of the alphabet transitions. So in this case, because the alphabet is 0, 1, each state has exactly 2 transitions. And it has 1 for 0 and 1 for 1, right? So we can just check that visually. We can inspect and convince ourselves that this is definitely a DFA. The last thing is, what do we do about final states, right? So final states, the final states in the DFA, right? So the final states in the DFA are going to be the set of all states that contain at least one final state from the NFA, right? So set of all states that have at least one except state from the NFA. So if we go back to our NFA, we see that Q2 is the only final state. And so the only set of states that contains a final state is Q0, Q2, because it contains the state Q2. And so this becomes a final state. There's an additional caveat that I want to mention. So there's a caveat here, is that if the empty string is accepted by the NFA, it might not always be that Q0 is the accept state, that S0, the initial state in the DFA, is the accept state, is an accept state when it actually should be. And so if the empty string is accepted by the NFA, you should also make S0 an accept state. Okay? Okay. And that's essentially an example of how to convert NFA to a DFA.